Okay, we will start in 1 minute.
Got it.
Okay. Hello, everyone. Welcome to the 141st Nice Talk. This is 9 p.m. in New York time and 10 a.m. in Beijing time. And today we're very glad to be able to invite the speaker Hao Kang. And he's going to talk about a very recent agent efficiency, agent acceleration paper, ThunderAgent, which can accelerate LM agent inference by 4 times faster. And I'm today's host, Wenyue Hua. So Hao Kang is a third-year PhD student at Georgia Institute of Technology, advised by Tushar Krishna. He's currently a visiting researcher at MIT, collaborating with Song Han. His research mainly focused on training and inference system for large model agents, agent-based financial trading system design, and asynchronous parallel algorithms for agent system. And I am Wenyue Hua. I'm currently a senior researcher at Microsoft Research. Okay, so now let's give time to Hao Kang to give this talk.
Well, thanks, Wenyu, and thanks for everybody in NICE and holding me here. It's an honor to give this talk about our recent work, which is called ThunderAgent. It is a fast, simple, and program-aware agentic inference systems. And today my topic is about like so just let me. Yeah, today I'm going to give a talk about like a new paradigm shift of large language model infra from the chatbot serverless serving to agentic serving. And like to describe this kind of paradigm shift, one biggest thing that people will ask is about like what is the agentic workflow and what is different like from agentic workflow and large language model chatbot services. It is about synergistic resource management and program-aware life cycles. So let me give a brief example of how agentic workflow looks like and what they do. So most of the agentic workflow nowadays follows the React paradigms, which they conclude of multiple conversations. So the problem is transferred from like a single term math and reasoning problems to a very compositional task like solving a GitHub issue or trip management, which needs multiple conversations. So in here, the large language model just does not generate the answer directly, but they need multiple steps of reasoning and inferences to achieve the goal of the tasks. And second is about tool calling. So previously, when large language model tried to solve the math and reasoning problems, they usually seldom calls the tools, and even they calls like the calculators. They do not interact with the environments through the tool calling. However, for agentic workflows, it interacts with the environment with tool calling, like compiler when we are coding, and and other remote tool callings or model callings. So when agentic workflow is executing with large language models, we call it reasoning phase. And when it is executing with tools, we call it acting. So this agentic workflow, they're shifting between reasoning and acting till the goal of the task is achieved. And they does not happen together. They happen synchronously and in a linear growing trend. So if this is the agentic workflow in your system view, what is the difference from the previous like single turn generation or chatbot serving? The first problem is that it's about KV cache locality. We all know that the KV cache is one of the most important problems for large language model serving, and here the biggest property of the agentic workflow is that the requests in the program, in the same workflow or in the same program, they just add up to each other, and this continues to grow. Like the previous end request of the program, the KV blocks is on the left, and the current request needs the previous KV catch blocks to generate new sentences and the new thoughts. And the ongoing or the future request will need all the previous KV blocks as well. So the multi-thread conversation has a very high catch hit rate among requests in the same programs or the same problems. And the second is that the tool, since the agentic workflow, they need to interact with tools and interact with the environments. They need to execute tools, consume different resources, and in a very complicated way. So let me give you some examples. So some tools, they consume GPU. So basically, they are either large language model parameters or they are large language model KV catches. So they are either shared between programs. All the programs need to execute it based on the same large language model. So they share the large language model parameters. However, the KV catch is different in each programs. And some resource, they consume CPUs, like the database. They are sharing between the programs, and they are retrieved and shared by all the programs. And like for the Docker and the sandboxes we are using for coding agents, they are shared in each programs, but they do not, the programs does not share with each other with their Dockers. And there are probably some request level tools like terminals. And some tool called, they consume resources in disk, like SSD as well. So different tool life cycles, like they are either sharing between programs, they are whether shared in each programs, or they are request level, and they consumes very like different kinds of resources. So this tool called resource management is another very big problem. And okay, so this is the problem we have. This is the paradigm shift, and this is the program. But if we are running the agentic workflows on vLLM or SGLang, which is a very successful state-of-the-art large language model infra, so what is insufficient if we are running agentic workflow on it? So the first problem we identify in our paper is called KV catch thrashing. This leads to very heavy reprofilling of each program and each request. So why this happens? So what we know is that like multiple conversation has a very high catch hit rate among requests in the same program or the same problems. However, the current large language model infra, they applies least recent used algorithms for KV catch management. So let me give an example here. So so the green bar is the GPU HBM. It is all the memory we have, and most of it is used to store the program's KV catches. So we see that the GPU HBM are occupied by the program's KV catches. So the yellow is other programs' KV catches, and the blue one is the acting workflows KV catches. So when it is acting, it is not executing on GPU. So the current the current SGLang or vLLM, they see it as a unused KV catches. So when another program, which is program 2, which wants to reasoning, and program 1 is currently acting, the eviction policy will delete all the program 1's KV catches, and programs 2's KV catches will occupy the memory. And when the program 2 finished the reasoning phase and is turning to the acting phase, which is it is acting with tools. So it is seen as vacant. It is seen as unused KV catch as well. And this time, the first programs will return to the GPU and will need to reason again. But this time, since the program's one's KV catches is already being evicted, it cannot find its KV catches, and so the first programs will need to reprofil again. And this happens again and again between the programs and increase the end-to-end latency for each agentic steps. So I could give you a profiling results on single node H100 when we are evaluating the GLM 4.6 models on a single node. So we found that like with the x-axis is the parallel workflow number, which is how many agentic workflow are executed together. So you can see that with the number keeps going on, keeps increase, we found that the end-to-end latency of per agentic steps increases a lot from like within 10 seconds to almost 60 seconds. This is almost 6 times increases because of the heavy reprefuel happens in each agentic steps. You can see the prefix catch hit rate continues to decrease from like 60% to about 20%. This means that the program's KV catches are evicting with each other, and there's a very huge KV catch threshold here. That's the first problem. And the second problem is called the memory imbalance among GPU nodes. So what we know is that like the multi-turn conversation, it has a very high catch hit rate among the requests in the same program or the same problems. And they tend to route requests in the same program to the same nodes because the KV cache is stored on that node. This is called KV-aware routing. It is currently used by vLLM and SGLang. However, this kind of routing strategy, it ignores the load balancing problems of the multiple nodes. So so let me give an example here. So probably we currently want to decide this program, whether it should be routed to the first node or the second node. And we know that previously, this program is always rotated to the first node because we follow the KV aware routing strategies. But we found that probably the first node is currently occupied with a lot of reasoning programs. However, the second node is currently almost empty. But since we apply the KV-aware routing strategy, it locks off the ability to transfer program among nodes. So the node 1 will cause great KV cache thrashing, while node 2 is underutilized. So this is the memory imbalance problem when we apply the KV-aware routing strategies to current large language model infra. And through our experiments, this is a very huge problem. So we are serving the agentic RL rollouts among 2 H100 nodes, and we found that great memory imbalance problems. So you can see that in this graph here, so the axis refers to the executing time, and the y-axis refers to the memory usage. So in a non-thrashing situations, we found in vLLM KV-aware routing strategy, we found that the memory difference can exist to like over 50% of the differences. So this is a huge memory imbalance between these two nodes. And third problem is kind of easy. So current large language model infrastructure does not have a effective tool resource management. And if we are using Kubernetes, like we do not have the information of the agentic program status. So the current large language model infra, they cannot distinguish the acting program or finished program. They does not know whether this program is ended or they are actually currently acting with tools. So the sandboxes in coding agents and other agents, they're usually not restored and left on CPU memory and disks. So you can see when we are proceeding with more agentic workflows, which is the x-axis in this figure, so the disk usage continues to increase because there is no or garbage collection of the current agentic workflows. And if we can apply a very actively, so if we profile what is the active disk usage in the current situation, you can see it is almost a small constant. So this means that a lot of disks are not used and is currently occupied by unused Dockers and Sandbox and other tools. So with these three problems, like I want to make a conclusion here. So the current large language model infrastructure, they lack of a high-level abstraction that can retrieve the agentic workflow status. Like we do not know whether they are reasoning, or they are acting, or they are finished. And they do not have a synergistic tool resource management. Like how do they manage the CPU memory, the disk memory, and the internet ports? And the scheduler, actually, they cannot identify KV cache locality of programs, and they cannot manage the tool resource efficiently because of the lack of the high-level abstraction. So yeah, so after seeing this, like a problem came out that came out that like how should we design the abstraction to help solve these different problems. So so a lot of papers are talking about this, like Outflex and Continuum. They're focusing on like to make the they're focusing on like describe the GPU resources from the agentic workflow as a program. But here, what we see that is that like not only the GPU memory should be managed in a program-aware scheduler, the tool should be managed in a program abstraction as well. So in here, we gathered all the resources that an agent might need to describe it as an agentic program. So you can see that this is how we describe and design our program abstractions for any agentic workflows. So the first one is called program identity, program ID. This is used to link all multi-turn requests from the same agentic tasks into one unit. Through this ID, we know, okay, so which request belongs to which program. So this is different from vLLM's multi-turn like user ID, because like the program identity not only describes the request and the KV catches, identify them like which program it belongs to, but this program ID also tells which dockers belongs to which program identity. So this is not only this identity is not only used to track the GPU's status, but also the CPU and the remote status. The second is the context length. So this is used to track the KV cache footprint of each program in real time. And this contributes to how we calculate the KV cache size of each different programs and how we schedule them. And the third thing is called tool environments, which is a set of tool resources like containers, sandboxes, like and internet ports and remote APIs, so bonded to this program and used in this program. So this is used to reclaim the resources when the program terminates. And the fourth thing is called backend location. So this is used to describe, okay, so which this resource, program's resource is located in GPU, the number of GPU nodes. So this helps us to route requests to the same nodes for context locality and help us to route different KV caches to different number of nodes. And the fifth thing is called execution phase. This distinguishes the GPU's the reasoning from acting, which is a sole design in our agentic program abstraction. So so the agentic currently have two different execution phases, which is GPU large language model reasoning and tool acting. Where reasoning they are GPU bound and acting they are tool bound and they do not execute anything on GPU. And the last thing is called scheduling state. This is this is completely different from the execution phase. So scheduling states means that whether they are currently being executed, like active, or they are paused for our caused by our scheduler, or they are terminated, they're finished, and the program is terminated and the problem is solved. So through these six features, we can know that the program, like how many tools it used, and what's the context length, and what is the GPU locality, KV cache locality, and we know like how should we schedule the agentic workflows. And okay, so after we have this abstraction, we must know, okay, so what is the cost of model, or we should say, what is the thing that we are trying to optimize? This is quite different from like traditional large language model serving engine, because like traditional large language model serving infra, they takes all the computations as effective computations. Either they are pre-filling, they're decoding, or as long as they are computing and there is no idle and there is no waste here. So generally they use token per seconds or GPU utilizations as their cost model. And it is the thing that they are trying to optimize. But however, in agentic workflow, things are quite different, because like pre-filling, when we are evicting these KV caches, and we need to reprofil the program's KV caches. So it is a computation loss, though the reprofilling will increase the GPU utilizations because they're executing heavily prefilling. So in this way, we need to design a cost model that will identify and distinguish the waste of computation and useful computation. So in total, the cost model can be separated into these 5 parts. So the first part is cost of decode, like how many resources are used for large language model decoding. So this is useful. And the second thing is called like the cost of prefill, which is how many resources are used for large language model prefilling. So decode and prefilling, they are useful computations. However, the cost of reprefill or recompute is totally a waste. So this is the thing that we want to minimize. And the cost of unused is that like is usually caused by the memory imbalance, that some of the memory or resources are not used by the current agentic programs and is currently idle. And the last thing is called caching, which is related to like how many GPU caches that we stored on HBM, whether we pin them or we just keep them there. This will cost some. This will create a new cost since we want to keep the KV cache hit rate high and reduce the cost of recompute. So there are 5 parts, but actually, so the prefilling is a very small part compared with other 4. So we generally take the decode, recompute, and unused and caching cost into our considerations. And our optimization goal is to reduce the recompute cost, caching cost, and unused cost, which will improve the prefill and decode cost. So another problem is that like the prefilling and decoding actually in executing, they are delaying with each other. So let's say we are decoding with tokens, we're reasoning, and there's a new request coming in which needs to prefill. So this will delay the decoding phase. So in this, so because of these problems, we need to design a cost function that can separate the effect with each other, with the interaction with each other. So what we do is that we calculate the memory instead of the computation cost as our cost model. So which is called a space-time product. This is actually used by like a lot of service company that how they calculate the price of the serving and how is the how many resources is consumed on the hardware. So this is the integral of the used memory and time consumption. So let me make an example here. So for example, the decoding, the cost, the STP cost of decoding is that the KV cache memory used for decoding and the time multiply with the time of the decoding. And preview is have the similar effect as well. So this is how we design our cost model. And with this cost model and with this abstraction, how do we solve the problems that we have mentioned about KV cache thrashing, memory imbalance, and tool recycling? So the first problem is about, okay, so KV cache thrashing will cause a very heavy reprofilling, and this will make the end-to-end latency very, very bad. So a big huge difference that the abstraction brings us is that how we can see the acting program's KV cache. So let's see here. So request level large language model infrastructure like vLLM and SGLang, they can only see the reasoning program's KV caches, which is currently occupied KV caches and is used for prefilling and decoding. However, they cannot see the acting program's KV caches because these programs are interacting with tools, and their KV caches are idle on GPUs. So the request level large language model infrastructure see this KV caches are unused memory, and they are usually being evicted. However, through the abstraction, we know that the state of the program is whether they are reasoning or they are acting. So the program-aware agentic infra, it knows how many KV cache space will be used by acting programs as well. So through this case, we know that whether it will thrashing because we take the acting program's KV cache into consideration as well. So if the total GPU memory, HBM memory, is smaller than the reasoning program and the acting program's KV caches together, so the thrashing will happen in near future. So we periodically detect whether the program's KV caches, including the acting program and reasoning programs, whether they exceed the GPU memories. So why we want to periodically detect the GPU memory? The reason is that so previously like vLLM and SGLang and other like agentic infra, what they do is that they are heuristically on tick to detect whether the memory exceeds the GPU capacity. But the problem, let me give you an example. So there's no new program coming into the GPU memory, but the program themselves are reasoning, and the context will grow further. So even no new programs comes in, the GPU memory can be exceeded by the current program KV caches as well. So that is why we periodically detect whether the program's KV caches exceeds the GPU memory. And another thing is that like if the KV cache exceeds the GPU memory, we pause the program and delete them from the GPU to avoid thrashing. So this gives us another problem. So if we want to delete or we just evict this program, we pause them. We prevent them from going into the GPU. So what kind of program that we want to evict first? So we have, so this is a very complex problem. We need to have some assumptions. So our assumption is that we assume the tool calls are not predictable. We only take care of the cost of recompute. This is because like we have profiled different agentic workflows, let me see, coding agents, like scientific agents. So, and we found that so for coding agents, their tool calls are usually predictable and takes very short time. But for kernel agents, CUDA kernel agents, or scientific agents, their tool calls are usually long and not predictable. And not only for these complex agents, but also like for some tool-use agents like Tool Orchestra, which they use the remote model API. So like ChatGPT and the Cloud, we do not know how many times it will take for this tool call. So to make our agentic infra more universal, we assume that tool calls are not predictable, and we only take care of the cost of recompute here. So what is the cost of recompute here? So it is, through our calculation in our paper, it is proportional to the square of the context length. So this is matches with the actually the flops of preview, which is the square like it is not linearly, but it is the context length square. And so if this is our cost of recomputation, this optimization problem is very easy. That we want to parse a constant memory, and how do we choose the programs with different context lengths? So to achieve the minimal cost of recompute. So it seems that like parsing the smallest program has the least cost of recompute. This is proved in our paper. You can use Cauchy inequivalence and other methodology to compute. That is very easy. So through these things, like we know that we have to use the smallest first parsing and restore strategy, which is that we usually, when thrashing happens, we usually parse the smallest programs. And when the GPU is idle and there's enough spaces, we usually like put the program with the smallest context into the GPU again. So then and there's some other designs here. So for example, so we usually make the new program, which is step equals to 1, has the smallest store of restoring, which means that they usually are not taken into consideration into GPU reasoning unless all the old programs are executed. This is because we want to make sure that the end-to-end execution time of each program will not be eliminated or will not be delayed, because like the new program, they always has the shortest KV caches, and they are consistently putting into the execution phase. And there's a lot of programs that are executing, but none of them are finished. Through this, yes, we avoid thrashing and reduce the recompute cost. And the second problem is that, okay, so for the GPU node scheduling of agentic program, we design a global waiting queue for them. So what we know is that like the requests in each program, they have KV cache locality, which means that the KV cache hit rate is very huge in each request of the program, but the request among program, they actually does not share similar KV cache. This is because like different program, they have different tool calls and their KV caches are different a lot. So from what we know, a very interesting, a very easy trade-off is that like a very easy Pareto trade-off is that like we use load balancing among programs and KV-aware routing in each request programs, which means that like if this program is paused and it will be redirected to another program, we think that the locality is already broke because of we paused this program, and we just assign this, we just restore this program to the GPU node according to the load balancing and memory imbalance situation among different GPU nodes. But if they are not paused, and this program is currently active, we always assign the request in this program to the same GPU nodes. So this gives us the ability to transfer the different programs to different nodes and make the whole workflow, inference or rollout more balanced and give us better throughputs. So about the tool resource management, like it is very simple as well. So what we know is that the sandbox's life cycle, it ends with the programs. So we just have a hook-based garbage collection. Whenever the program is terminated, we send the signals to the tool resource management, and we delete the sandboxes with its images to save the disk and the CPU memory. And another thing that we have done, which is quite engineering, which is that we allowed asynchronous environment preparations. This is because like we found that like building Dockers and building sandboxes, it usually takes about like 1 minute or more in program executions. But we found that actually even the current program is waiting and the other program is executing, we can prepare the environment in advance, like downloading the Docker or prepare the building the images and Dockers. So we allow the async execution between GPU reasoning and tool execution. So this further gives us better end-to-end latency of the system. And with all of this, like we here comes the experimental results, and we have like tested a lot of agentic workflows, including serving, inferences, and rollout, agentic RL rollouts. We have tested on multiple GPU nodes. So you can see here, so the experimental setting of agentic workflow is complex, is more complex than other things because we have different dimensions. So we have used 3 kinds of model here. So the first one is SGLang 4.6, which is about like 355 billion parameter models, which is quantized into FPA for better efficiency. And then we use Qwen 235 billion MOE models. So the previous are 2 very big and it is used in a lot of commercial cases as well. So the third one is called Qwen 3 80 billion model. So this is quite a edge model we are using in tool orchestra. So we cover the server scenario and edge scenario. And for workflows, we have profiled on agentic workflow, we have profiled on mini SWAgent, which is a very efficient, it has a property of very efficient terminal tool calls, where the tool calls are very efficient and it usually takes within one second. And the second is OpenHands. It has a very heavy tool calls and not only works for coding, but also works for scientific and other use cases like computer use agent and other usage as well. So they conclude quite heavy tool calls. So generally OpenHands executed tools like with between 1 second to 1 minute. And the third thing is called tool orchestra. This is a remote, this is a paper from NVIDIA, and they have a very small model on edge and they call the remote very strong models remotely. And this workflow has a property that the tool calls is totally unpredictable. So for benchmarks, we are using SW bench, which is a coding benchmark used by most of the people, and scientific bench, which is a science agent benchmark. And the last thing is tall bench, which is a tool use benchmark that helps people to buy to recommend people to buy this the stuff in website. And you can see it here. Here's our results for inferences. So we have tested different models and different agentic workflows on single H100 nodes. You can find that through these 6 settings, our methodology called ThunderAgent exceeds can provide better throughputs from 1.2 times to 3.6 times, and it is better than vLLM and Continuum. And another thing which is very interesting is that it is not only about the throughputs, but another thing is that our methodology maintains high throughputs in high concurrency in serving scenarios. So you can see the x-axis refers to the parallel workflow number. When it increases, all other methodology like vLLM and Continuum, they are decreasing because of this parallel workflow makes the thrashing problems so their end-to-end latency decreases. And however, our methodology maintains high concurrency whenever how many workflows are added into the system. So this makes our system very robust to practical use cases where you do not know how many workflow you should put into your machine, but you can just put as much as you can. So our methodology can keep a very high throughputs whenever how many agentic workflows you are putting into the agentic systems. And another thing is about the KV catch heat rate. So you can see it here. This aligns with the previous figure. So why we have a very high throughput in high concurrency is that we maintain a very high KV catch heat rate in different workflows and different agents. But you can find something interesting here. So in figure C and figure F, so you can find that our KV catch heat rate is worse than Continuum, but still better than vLLM. And this is because we have our methodology can do an autonomous pre-DOS. Which is that, let me give this example. So let's say probably one agent workflows, their a tool execution takes almost 1 minute. So if you want to keep the KV catch heat rate very high, you need to keep this KV catch on HBM. So this causes a problem that if you keep this idle KV catches on HBM for over 1 minute, this will have a very low GPU utilizations. But our methodology can autonomous do the trade-offs to decide whether the tool call is too large that we need to evict this this KV catch of the programs to give the space of other programs, or we keep them on GPU. So this autonomous trade-off can have lower KV catch heat rates, but still their throughput is better than other methodologies. So another last result is we have tested our agentic rollouts on GLM 4.6 on 2 H100 node, and in each node we use tensor parallelism with degree of 8, and between nodes we are using data parallelism. This is a very practical use case, and we have found that our results are better because we are balancing the workload between nodes of agentic programs. So it provides us from 1.8 accelerations to almost 4 times acceleration. Yes, and thanks. And this is my report. And I want to say something for this future of these projects, that we do not only want to build it as an academia project. We're currently collaborating with Together AI for their agentic data synthetic, which already provides 4 times better throughputs in data generation. And we are going to post a blog before the end of this month. And we are collaborating with Skylab that we are collaborating with one of their project called SkyRL. We are accelerating their code bases as well. We are going to have a blog post as well, and we are going to take these projects to NVIDIA in future, like to see if we can benefit all the community of agentic infra community to give us a better agentic infra system. Thanks.
Okay, thank you so much for this like very, very interesting, very dense talk. Yeah, I quite enjoyed this talk. Thank you very much for this. So okay, so we have like about 20 minutes for Q&A. So for people from like WeChat, YouTube, we'll see like questions. So yeah, so first I have one question. Like okay, one question. Like first question I want to ask is a more clarification. So like you're talking about there were like three issues of this like old like vLLM SGLang serving. So I'm wondering about the second one. So like I got a little bit lost on the second one. So I'm wondering if you can like clarify this.
Sure, no problem. So when we are routing a program or requests among the GPU nodes, we need to care about two things. The first thing is that where is the KV cache of this program? Because if we do not take care of this, so whenever when we are routing the program or request to different nodes, we need to reprofile again. And because like we are routing to a node that it does not have this program's KV caches. And another thing we need to care about is called load balance, which is that like how many programs are currently running on each node and how many memory are occupied in each node. So when we are caring about two things, like we need to do a trade-off. So how do the current large language model infrastructure do the trade-off? So for vLLM, it only cares about KV-aware routing strategies, which means that they don't really care about load balancing. They always assign the request in the same program to the same nodes. Let's say I'm assigning program A to node 1 and I never change it. So this causes a problem that some programs are not filled with nodes are not filled with programs, but others are filled with a lot of programs. And since they do not care about load balancing, they never routing the programs to a different nodes. So this is this is very bad. And second, what SGLang do is that it is building these things based on heuristic algorithm. So what they do is that if the nodes are not unbalanced, let's say if the unbalancing is within like 20% of the imbalancing, we are routing according to the KV-aware router. But if they are the imbalance is over 20 or 30%, they are routing according to the load balance router. This is not the optimal solution, and it also needs you to change the heuristic waterline among different agentic workflows. So both of these problems, they are not very autonomous routing, and they are not doing a great job. So that's the problem that previous infrastructure has. Yeah.
Okay. Get it. So basically, so like the traditional like serving, they only care about like this KV cache. And then in your system, you also like care. So when you move like different programs to different nodes, that basically require a recomputation. Is that or it?
Yeah. So currently, since we are not enable KV cache offloading, but it should be enabled in future, we need to recompute when we are routing to different nodes. Yeah.
I see. Yes. Yes. So this is kind of related to another question that I have, because I noticed that in your like in the current system, basically you care about like this recomputation. So I'm wondering like because I think swapping is also like a common like choice how people usually deal with like KV cache. And so I'm wondering like whether that's kind of in the roadmap or like for now you intentionally think this is not like a good idea, so you drop it.
Yeah, definitely it is in the roadmap. And I think like this, so when we are talking about like transferring KV caches among nodes, and if we are swapping offloading them to CPU and disk, that is definitely good choice, and it is better than recomputation. And I think that is orthogonal to our scheduler, because like that is only we just need to design a different cost, because we need to reload or we need to transfer. This is transfer or reload cost. So can be combined with our system as well. And currently we are collaborating with Skylab, and we are building a new agentic memory system that combines really well with this agentic scheduler. Yeah.
I see. Yeah. So I'm wondering, because so this, like, whether you choose to do this recomputation or like whether you choose to do the swapping may also be like very workflow or program like specific. So
Exactly.
okay, cool. Okay. And okay. So another question that I have is, so in the current experiment, I can see that like basically the experiments are done like in specific data sets. So like it's either a coding task, or this is like scientific task, etc. And then in your like the future of the project part at the very end, you mentioned that you are like already incorporate with Together AI to accelerate data generation. So it
Yeah.
sounds like the current serving work really well with like a single workflow or like similar workflow scenario. But in real serving time, you can have like a mixture of workflows. And then I feel like how you schedule different workflows, different programs can be very sensitive on like on that as well. So I'm wondering like how
Yeah.
currently you're dealing with this.
Yeah, I want to ask this question as well. Like, I don't think in current commercial uses, we need to serve different workflows in the same cluster. Let me give an example.
Mhm.
So when cloud, they are building their code agent, they don't serve with their healthcare agent as well, right? They just give a very big cluster serving the cloud code. They do not use cloud code for healthcare, right?
Mhm.
So it is always the same. And this is for serving. And for training, generally for agentic RL training, we
Training,
want
yeah.
to, yeah, we always have the similar workflow. So probably we have, and we could have a different workflow combined together and serving together. But I don't think that's the use case for now. But even if this in future, we can design, like, we can modify, because this abstraction is very universal, we can modify our scheduling strategy to fit for that. Yeah.
Yeah, I feel like if you see from the server side or like say the business side, it is usually the case. Like you have this cloud code or you have some like health system that's served
Mhm.
and then people just send a request. So it's a very reasonable, say like one cluster always or like almost see always the same like same workflow.
Yeah.
But another scenario, I'm not sure like whether it's happening now or that I have in mind is that like people can deploy their own agent or like different like merchants can deploy on like the same platform. For example, like Together AI. Oh, okay, it's not like a good example, but basically, it's that like yeah, there can be like a platform where like a cluster where we invite people from like communities to build their own agent and then serve them.
Yeah.
And then in that scenario, you will actually see like very different workflows. And I think there are like companies doing that. So it's basically like a community type of company,
Yeah.
where you have like several hundreds different like merchants, agents that's active in their
Mhm.
cluster, and then you will see like very different workflows.
Yeah. Yeah, I totally agree with that. Yeah, I think like personal agent is a different use case. Yeah.
Okay. And is that in the roadmap, or for now you are like your team is mainly focusing on, say, like this cloud code serving, things like this?
Yeah, we believe that like if we focus on training tasks and like single serving task, it will make our project grows faster for now. But probably
Yeah.
we are considering and at it for future. Yeah.
Okay, makes sense. Yeah. And one thing I'm wondering, like when I read your paper, is that so I think this program level abstraction, this concept came pretty early. I think late 2024, early 2025. There are already papers that's trying to accelerate, like not language model, but agent. So I'm wondering, can you do like a deeper dive of the literature review, how your system differ from them? and
Yeah.
why it is better. I'm assuming it is better.
Yes, sure. So first, that I think like some similar questions are asked on Twitter as well. But here's the thing. So I think that previously they only focus on GPU resource management. Like they only care about KV cache. So if you take their program abstraction into consideration, I think they only have program identity and context length. They does not have the tool environment, backend location, execution phase, and scheduling state. So that's why they are building their program abstraction. And if they are building that program abstraction, I think they are trying to make the agentic workflow looks like a multi-turn conversation. Because multi-turn conversation have multi-turn interaction as well, but they do not have a tool execution and waiting and unpredictable waiting time. So we if you want to describe an agentic workflow, you must add the tool environments, backend location, execution phase, and the scheduling states into the program abstraction as well. So I think that's the most different thing that we are different from that we are building a synergistic system that managing not only GPU resource, but also CPU resource, remote resource, and disk resource together. And we does not only care about single node performances. Our methodology works on. We actually in paper we have tested on 2 nodes, and in the newer like the blog is going to post it like with Together AI. We have tested on 8 to 16 nodes. So we are more like an industrial product that works for a lot of clusters. Yeah.
I see. Okay. Okay. Okay, that makes sense. Okay, yeah. Basically, like the previous I knew about Autolex. So that's like my knowledge of this agent serving kind of stuff like there. Until I see this ThunderAgent. Okay, so
Yeah, I think Autox is already like surpassed by Continuum. Like I think they're coming from the same lab, and I think Continuum is a very good work that they open source their code, and I think this is not stop anywhere. I think there are a lot of things to do. Yeah.
Yeah. Okay. So another thing that I'm wondering, so which I think is like, for now, of course, like kind of out of scope. So now like projects or papers about agent memory are like so like there are so many of them, and people do, and agent is very famous to have very long context, as you must have known. So there were different papers showing like, okay, how can we do like a memory eviction, how to do like memory summarization, compaction, etc. So I think that stream is also like a very like heated up domain, how to, well, so they are mainly care about like this memory or context sense, but like in another sense, it is also about like speed and efficiency. So for this, I'm wondering whether maybe in the roadmap you will consider, say, how this agent efficient serving can be compatible with like update of memory, like how in a single program the KV will be evicted by like by
Mhm.
the program's own decision, etc.
Yeah, I think the agentic memory. Yeah, there are a lot of people discussing about it, but I think like the biggest I think I do not understand is that they usually do not open source their code, and they do not tend to combine with very good agentic chat like serving infra like vLLM and SGLang, and they are just claiming, okay, I'm the first to do this, I'm the first to do that. I think it makes no sense. I think the system researcher should do things that like benefit to the community. I think they need to open source their code, and I think that's the first part. And second part is that I think I don't think that there is a universal or programmable scheduler or programmable KV cache like offloading, transferring tools that is currently being invented for the whole community. So we have done a lot of studies and tests on non-React agentic workflows and also React agentic workflows as well. And we found like previous offloading strategy works not that good. So I think like let's just stay tuned, and I think we are going to have a lot of new things in our new project. Thanks a lot.
That sounds very cool. Okay, I'm very much looking forward to this.
Thanks.
Okay. So yeah, another question I'm seeing is that I think towards the end of your talk, you mentioned like 3 models that you're currently testing. So one is this Quan 3.8b, which is more like an on edge model. It's like a much smaller model than others. So I'm wondering so again, this can be very out of scope. So on different devices like GPU, like on GPU, on edge, or like even like very small, like say mobile, like for different devices, how are you considering like say this agent only for large cluster GPU serving, or you also consider like a smaller, like small device or edge device serving?
Yeah, so I think we are not that edge, but we have tested on 2 kinds of devices. The first one is H100 clusters. That's a server and very big. However, like we have tested our Kun 3.8 billion models on RTX 5090, which is a game GPU card. Yeah. So I think like, but I want to say that I think in edge, like throughput is not a very important feature, because generally when we are trying to deploy agents on edge, the batch size is not large, but end-to-end latency is very important. Yeah.
Okay, cool. Yeah, and then also because another question is so in your experiment you basically test different workflows like coding, science, etc. So so I'm wondering, for different workflows, do you see different bottlenecks?
Very different.
Okay, and do you think that need like like per workflow serving or etc. Like how you're dealing with like this diversity of
so that's why I'm saying like self-evolving and programmable is 2 very important part for agentic infra systems, and that is why we want to build a programmable agentic memory system, and as well we are going to make ThunderAgent programmable and self-evolving, because different agent workflow differs a lot, but that does not mean that we need to write each workflow an agentic infra. Probably you want to do that, that's okay. But what we are trying to do is that we want to make this algorithm or scheduling algorithm or offloading algorithm evolving with the environments, and it can tackle a good scheduler for different workflows. Yeah.
Okay, wait. So what do you mean by evolving with environment?
Yeah. So basically, we can gather the information when we are running. And we can detect the bottlenecks while deploying the agentic workflows, and we can adapt our scheduling and offloading strategy according to different workload.
I see. Okay. So is this like auto detection and like auto change of the of like of methods like a new feature, or a new feature is like specific to like ThunderAgent, or it is already like in others as well?
Yeah, I think this is one very important thing roadmap that we are going to do in ThunderAgent, and also we are going to show this kind of thoughts in our new agentic memory paper as well. Yeah.
Okay, that's cool. Okay, so I think that's all the questions that we have. And it's almost time. Thank you very much for this very interesting talk. And I can already see like a big future for this agent serving, which I think is definitely like the future. Like LLM serving is only like a very small part of agent serving, and agent is like much more diverse and much more realistic, and it will be like much more like widely adopted in the future. So yeah, thank you very much for this very interesting talk. And yeah, thank you for the audience. Yeah, okay.
Thank you very much. Thanks.
Okay.
Bye.
Bye.